This is a demo of the vised marks extension for EEG Lab. This extension is designed to hold annotation information in a new structure within the EEG structure called the mark structure. This can hold information in the time domain, across channels, and across independent components, and is meant to be extendable so annotation of new measures is easily added. It's also designed to work with the branch of the EEG plot window so you can interact with the information while you're scrolling the data. So let me just load a data set here. And here. Now, once the extension, the vised marks extension, is loaded into EEG Lab and you have a data set, there are a few menu items. In the File menu, there's the vised configuration. This is where you can store a bunch of information about how the scroll window will interact with the mark structure. In Tools, there's also the Marks menu, which has options for epicking and concatenating data to go back and forth between segmented and continuous data. There's editing marks information, so you can collect different things together and combine marks, and then you can also select data based on the information that you've gathered into the mark structure. Now, one of the first things that we're going to do is we're going to build a mark in the time domain for this particular data set. And what we want to do with this mark is basically just annotate where a certain task is currently happening. And then in the edit window, we'll use the visualize and edit in the scroll plot. I'm going to Tools, Mark, and I'm going to edit some marks, and I'm going to do what's called mark an event gap. So what we want to do is we want to look at events in the data and then decide when there's a certain task on, and then build an annotation that we can visualize to say this is currently a specific task. So I have a recording that's appended two different tasks, a checkerboard left and right and a facehouse butterfly task. So what I'm going to do is I'm going to click on this event type, hit OK, and I'm going to remove any specific information about it, and then say that it doesn't have to be this exact label, anything containing these characters. Now I'm going to look for a gap between any two instances of these of 4 seconds. And what I'm going to do is once it finds gaps between these events, so there are FHB stimulus that happen every second or so, and also any response has these characters in it. So if there's a gap between any two of these that's greater than 4 seconds, it's likely a break or the task isn't happening anymore. So once it finds one of these gaps, I'm going to mark some offsets. So basically a distance from the last event before the gap and a distance from the first instance of the new string of these events. So I'm going to say 3,000 milliseconds to negative 3,000 milliseconds. And I'll show you exactly what this ends up meaning after. Now, what I want to do is I don't want to actually annotate the gap of these events, but actually invert it so that it's going to flag all the instances where these events are currently happening regularly. And I'm going to call this in task FHB. And I'm going to give this a color. And the color will be 0.7, 0.7, and 1. So this will be a light blue color. And once I tab over it, will show it here. So I'll hit OK, and then this will create a new data set. I'll call it in task. So it's butterfly. So this will have created a new annotation in the file, and I'll show you exactly what this means. So in the EEG structure, there's now a mark structure, and this mark structure has time information, channel information, and component information. Now, what we just did is we added some annotations into the time information. So here we go to EEG, marks, and time info, there's a structure that has a label, a color, and the flags. So if I look specifically at the second one, the one that we just added, called in task facehouse butterfly, we can see what the color is, and then the flags are basically an array of zeros and ones, and the ones indicate the time points where this annotation is true. So what I can do quickly, I can say figure plot EEG dot marks dot time info, the second one dot flags. And this is a basic visualization showing that these 3 periods of time right here are when that task is actually occurring. And then this drops back down, and then we can see that there's a second task that would happen over here. Now, once we have this structure, there's a new branch in this extension. There's a branch of the EEG plot that's sensitive to this structure, and we'll plot these as areas on the background of the figure axis. So I'm going to go to Edit, and Visually Edit and Scroll Plot. And this will bring up a new graphical user interface for plotting the data in the scroll plot. So we're going to plot EEG data, and we're going to change the Y spacing. So now these options that we see in this property grid are pretty much all of the optional inputs to the EEG plot scroll window. So I'm also going to plot 40 seconds. And some things here, there's the select command. So this is the typical select command. You can choose periods of time. The extended select, this is what happens if you press shift and left click. And the alt select is if you control and left click, or simply just right click. Now another thing that I've added here is that there's a key select command. This is a cell array of strings that begins with a character and then a command to execute. So what will happen is if you're scrolling over the data and you press this key on the keyboard, it will execute this command. And the VEEG plot is the branch EEG plot. So for example, if I press T, this will produce a top graphical plot. If I press R, it will basically redraw the entire figure. Now, I'll hit OK, and then I'll plot this, and we'll see what the first annotation looks like. So here's the data. I'll just get rid of DC offset. And the first annotation that we made, we can see is this light blue stripe in the data. And it's labeled right here as in task facehouse butterfly. And we can see that the duration that this is on starts 3 seconds before the first event of this type. And if we scroll through the data, we can see that it stopped during the break. Stopped 3 seconds after the last one, and then started 3 seconds before the new beginning. So this is how we annotate based on events in the data. And what we can do now, that was done using the graphical user interface, but here's a bit of code. In a few functions we can mark a whole bunch of other reasons just based on the events to flag when there are breaks, when the participant is just leading up into a task. So I'm just going to copy this code and paste it into the command line. Now that's updated, let me just redraw EEG lab. And we'll bring this plot up again. So it saves the properties that I've changed from time to time now that we're going to rerun it, and that's in a global variable. Now I'm going to add a couple new key commands. here. So the first one I'm going to add is the small character E, followed by VE edit, and then QEM, which is short for quick event make. So this will add the event called event. And then just for fun, I'll add a capital E, do the same thing, but add an event called event with a capital E. Hit OK. And this will bring up the same plot again. But now we can see that there are more annotations. Specifically, there's this new one here, this darker blue, which is the lead up into the task. Basically, this is a period of time that we might not want to analyze, but we might want to include in something like independent components analysis. This dark gray is non-task time. So this will also appear during the break, right here. And then we can see whenever the lead up happens again. Now, on the bottom there is another mark right here, and this is called the manual mark. This is one that we interact with, and the WinReg window of the ggplot is currently being told to mimic that specific marker. Now, with the key commands that I specified, what we can do now is if I go over the axis window and I press the key E, this will add an event with the lowercase e. But if I move over and I press capital E, then it will add event with capital E. So this is just a demonstration that we can now have a library of events that we can just add by clicking a key on the keyboard. Now, I can also, if I shift-click over this, I can still get the deleting functions. And if I shift-click over just any area, I can just manually add events as well. Now this is part of what was traditionally included in the vised plugin. Okay. Now, moving on, one of the important ways to annotate the data is using the internal artifact detection facilities that are included in EEG Lab. Although they weren't available for continuous data, if we can window the data and then concatenate it back together, we can see that that can be very useful. They're very powerful. So what I'm going to do is I'm going to epoch the data into regular intervals using the marks. And what this is going to do is I'm going to set 1 second intervals, and the windows are going to be from -0.5 to 0.5. So this will be 1 second epochs at a regular 1 second interval. And then I'm just going to call this C to E, continuous to epoch. Now, I can just plot this again, and then we'll see all the same information, except now this data is windowed into 1 second regular intervals, and you can see that by the dashed lines. Now, what we can look at here is actually we can use some. Although this extension is built to make it easier to interact with the data, it also makes it easier for testing new methods for flagging artifacts or capturing data, and then visualizing how that works. So what I have here is some code that goes through and checks the correlation coefficients between channels, and then determines from that whether a channel is a bad signal and that it has an unusually low correlation coefficient to its nearest neighbor. And then it also determines whether or not a channel is likely bridged to its neighbor by finding unusually high and unusually consistent correlations to its nearest neighbor. So what I'm going to do is I'm going to copy this code and I'm going to paste it into the command window. And this is going to go through and it's going to calculate all these correlation coefficients. And then with a single command, it builds a new label. So this marks add label will add new information into the mark structure that after this, whenever we visualize the data in the vised marks scroll plot, we can see the decisions that it made about these channels, and then we can work with them and interact with them. Okay, now that's done, and we just have to go to the marks, and then we'll plot it the exact same way. Now, actually, because we're looking at channels at this point, I'm just going to change a property of the time marks. This is the transparency of them, so I'm going to drop this down to 0.3, and then we'll be able to see the channel flags a bit easier. So now what we have here is we have the marks that are dimmed out in the background, but we've marked, based on the correlation coefficients across channels, channels that had unusually low correlation coefficients to their neighbors, and these are now grayed out in red, and we can see some bad channels grayed out in red. And then they also have these red tags along the axis pointing at the channels, the channel labels that they correspond to. And then we also have these green channels. These are the ones that have been flagged as likely being bridged to their neighbors. So we can see a few of them have been flagged for that as well. Okay. Now if I pan out, we can then go through and scroll the data. And then we can see that even though these criteria have done a pretty good job, there are some channels that it's missed, so I'm just going to right click on these. And then there's this one as well. And I'll scroll through a bit more. I'll actually increase the voltages to see if anything stands out. And there is a channel going back and forth over here. So we'll just see if there's a period of time where we can find that. And I think it's this one right here. There we go. So this has flagged a bunch of channels for automated reasons, and then we've been able to flag it manually as well, all the while knowing exactly why each channel got flagged. Now, what I can do is I can update the EG structure at this point, and then all this information will be stored. Channels for those reasons, for low correlation coefficients to their neighbors or high correlation coefficients to their neighbors, and the ones that I just flagged manually. We can tell what reason led to all of those. Now, another line of code that I'm going to add is this line that basically says that it's going to merge any channel marks for the low R or the bridging into the manual. So all of these channels will be grayed out on top rather than being red or green. And then that way it's easier to address. If I want to purge all the channels, I can just say get rid of all the manual ones. So at this point, I've done this calculation because the data were windowed, and I can go to marks, and then I can concatenate the epochs into continuous data. So this is going to bring everything together, and then we can plot this as continuous data again. And then, from there, once it's continuous data, what we can do is then we can re-reference the data and then filter it right after asking it to interpolate the channels based on what has been flagged. So I'm just going to zoom into this command right here, and then we can see that this is going to run the EEG interp function on the EEG structure. But what we can do is we can, in one command, give an input that's getting the indices of anything that's been marked manually. So this function right here is giving the command to return the indices into the interpolation function. So this will be epoch to continuous. And now if I simply run this function, this is interpolating the bad channels, and then we'll just take a quick look at it. And then this function will indicate the interpolated channels, and we'll just take a quick look at it. Okay, and now what we can see really is that the bad channels, I'll get rid of this background here, that the channels that we determined were bad are still gray, but they've been interpolated. So they look like fine data channels now because they're interpolated, but we can still tell what the problem was with each of them. So there's a couple channels here that were marked because they were bridged, and then a bunch here that were marked because they were bad. The gray tags here just show that those were flagged for some reason. The red and the blue, or the red and the green, are specific reasons, and then this blue tag means that it was interpolated. So we can keep all this information the whole time as we add more and more information to the rejection. Now, what I'm going to do is, after this we would filter the data, but I'm just going to load I'm first going to clear the data set, and then I'm going to load the filtered version so we don't have to wait for the filter. So now that the data are re-referenced and filtered, I'm going to segment the data again into regular intervals the same way that we did last time. So 1, negative 0.5, and 0.5. And this time, instead of trying to decide on bad channels, we're going to use the native rejection tools in EEG Lab to flag epochs of time, but then we're going to concatenate that back together and carry that data into the new mark structure. So the data are now windowed again. I'm going to go to Tools, Reject Epochs, using all methods. And I'll just enter some default stuff here. So I'll calculate the improbable data. And then after that's done, calculate the abnormal distributions. And then from there we can do the scroll data that's native to this tool. And we can see that it's been flagged in some periods of time. Particularly these, I think it's these nice and well. Okay, so I'm just going to update these marks. And then I'm not going to clear the marks or reject them. I'm just going to close this and keep the marks. So the rejection structure is intact. I'm going to go back to my marks plugin and then concatenate the data. So it's going to bring this all back together and then collect the rejection structure into the new mark structure. And once this is done, it has to collect all the events and re-gauge them to make sure they're staying right in time. And once this is done, we'll plot the vised window again. And then this way, in this one, we'll add some functions to the key commands that will allow us to interact with the annotations that were built from the rejection tool. So I'm going to copy these. Now this is E to C. Go back to the visual edit. Again, it'll have everything like it was last time. And then I'm going to add a couple more functions to the keys. So if I press S, it will do the select mark. So if I click on a specific mark of the annotation, it will automatically select that period in the WinReg window. And then there is the add a window mark. So once there is a WinReg selection with the blue background, I can add that period of time to any of my annotations. And I'll just show you how that works here. So here we have the annotations, and actually I'm just going to close this, redo it, and put the alpha back up so that we can see the time marks better again. So I'll put this up to 0.8 so that we can see them clearly. So we can see now that these annotations here correspond to the windows that were flagged bad. So what I'm going to do is I'm going to press the S and select this. And then I'm going to press M, and this will add that period of time to this final bottom annotation down here. Okay. And this annotation, called the manual annotation, can be used to generically flag things. Okay. Now, from here, I can update the EG structure, and then everything will be captured back to that. Now, that's a way of dealing with basic rejection, but this is also capable of dealing with artifact correction and interacting with two data sets, the original data set and the corrected data set. So one way that we'd really like to be able to do this is with the ASR handling of data. So I calculated a basic ASR correction, and what I'm going to do is I'm going to load it in and then compare the corrected data to the original data and build an annotation for periods of time where those two data sets are different. And then I'm going to plot that. And I'll plot it with some properties, some new properties that allow us to interact with the difference between those two data sets. So I'm going to copy this. This will compare the two data sets and build the marks. And now what I'm going to do is I'm going to rebuild this plot. And now that I've loaded the clean data that was generated, I'm going to plot as the overlaid data clean EEG dot data. And I'm going to copy some new key commands in. So these key commands there is C, which I basically use as correct, which is add a WinReg mark, and we're going to add to the ASR C. And I've also included the option called move data on. So if I select adding the mark to the ASR correction, what it will do is it will take the data from the clean data and it'll overwrite the original data with it, and we'll see how that works. Now I've also added the R option, which is basically remove, so that will remove that decision. And I can show you how this works here. So let's just show 20 seconds of data, and maybe change the micros to 80. Okay. So what we have here is now an overlay of the original data and the corrected. And this dark red annotation is now the periods of time where the clean data are different from the original data. Now, what I can do is I can select a period of time. And actually, let me just remove this background for a second. So I can select this annotation, and then now that this annotation is selected for a period of time when the ASR showed a difference in the clean data and the original data, I can press C on this period of time, and it will overwrite the original data with the new clean data. So we can see that during this period of time, it had it cleaned the data, removing the old data. Now I can also do this by just choosing manually an entire period of time, like this, and then on this period of time, clicking on C, and it will correct any periods of time in here that have been changed with the ASR criteria. Now, if I get rid of this, and let's say I decide that I'm not happy with how this correction happened, and let's say I want to let, for example, ICA handle this, I will click on select this one, and then sometimes it shows up black, not sure why, and then I'm going to reverse it, so I'm going to press R. And then at this point, it will add the original data back in for this period, as well as updating the annotation saying that this period of time wasn't corrected. And then from there, if any changing of the data is done using this interface, whenever I update the EEG, it knows to collect the right data back from the stream. So then, at this point, the key is really trying to keep the mark structure of annotations compatible with the size of the data array, so that the indexing will work. So there are tools for selecting data based on those structures. So if I go to marks and select data, I get this interface. So for example, I want to choose, I want to select data based on time marks, and then I can choose the marks. So let's say I'm going to select any mark with the label manual, and I'm going to generate the indices, and I'm going to remove these. So I'm going to remove any period of time that has been flagged for this reason. And I'm going to hit OK. And then I can do a similar thing. Select data and get rid of channel marks, and I'll do the same thing because everything was added to the manual criteria. That produced the indices, remove these, and hit OK. Now if we look at the data using the same plot, we can see that it's overlaying something here. I gotta get rid of the overlay. Get rid of the overlay data and plot the data that are left. And then we can scroll through and we can see that the data had been removed if I asked it to. In particular, this was one of the breaks. And then we'll also see that at the time when the task changes, the period of time we're gone. So here's the period of time when the task changes. Now, importantly, all of the annotations can stay, and you can keep building annotations for different reasons and different reasons. And as you purge data, the annotations will stay in line with the data set. Now, that being said, we can also use it for a bunch of other reasons. For example, once the ICA is calculated, even with Amica, we can plot that as well. So let me just load a data set that has that had Amica calculated on it. And what I'm going to do now is I'm actually going to load. So once you've worked with the configuration of your visual editing parameters, you can save the configuration. So I'm going to load one of these that I made for plotting the independent components of this other data set. Okay, and then I'll plot the figure. So I'm going to plot the independent components, and then this has a couple extra key properties added to it. One, we're actually going to flag independent components that are actually cortical, so the ACC or the occipital alpha. And let's just change this. So now what we have here is the activation of the independent components. The blue tags here actually represent independent components whose residual dipole fit was greater than 15%. So those automatically got flagged for rejection, and so they've also been grayed out. Now, clearly it missed some, so there are lateral eye movements that sometimes generate perfectly good dipoles. So the dipole criteria wouldn't catch that, but we can just, by right-clicking on it, flag it for rejection here. And likewise, sometimes there are perfectly good cortical components that don't have a good dipole fit, so we can invert those back. So even though this one doesn't have a good dipole fit, we can remove the flag for rejection. Now, another thing that we can do is, if oftentimes we want to see and highlight components once they've been classified for something. So there is a component here that is likely the ACC, and what I can do is I can click on the A key while I'm over this one, and it will highlight it in red. So this one is very interesting. In ACC, we can watch it as the task goes on for no-goes, and then we can flag other components that I've defined as the occipital alpha generators, and we can keep these highlighted when we scroll through, and of course we can just keep flagging other ones that we want to then purge from the data. Now, in this case, the red annotation is actually a continuous variable rather than just a 0 or 1. And this is the likelihood of Amica. So where this red bar is represents any period of time that was included in an Amica solution. And what we can do is we can find periods of time that were actually problematic for the data. And I know there's one over here somewhere. So we'll just go through and look at this. So in this case, right here, we can see that there was a period of time. Now, these blue bars were marked on an old measure that I was using that required two independent component analyses to run. The first one, it would just do a quick ICA, and then it would measure the amount of activation of the independent components in each time window, and then determine if there were too many components that were unusually active during a period of time, and it would flag it for this blue. And then after that, it would rerun another ICA, ignoring these periods of time. But what we can see if we include the likelihood array of the Amica is that Amica does a very good job at finding those periods while it's doing it. So what we can see here is the red continuous variable dims out during this period of time, which just means the likelihood of the model has dropped during this period of time. So in this way we can use the annotations also with continuous variables to plot measures to sort of test the, in this case it was a good test of the relation that these two measures had to each other and flagging the same periods of time. And then from there isn't much to say. So that's the vised mark structure, its current feature set that I hope to release soon.